want to spend a few minutes talking about another type of nuclear reaction. We've already talked about radioactive decay, alpha, beta, and gamma decay. Today I want to talk about fission and fusion, two processes whereby we can convert one nucleus to another, but are not natural and random. Nuclear fission is a process where one heavy nucleus splits into two lighter nuclei. This morning I asked about that word fission. Okay, where do we recognize that word fission from, or what does it kind of bring to mind? And somebody said fissure, like is an opening, right? Splitting. Okay, there's a fissure in the ground. There's fissures in the ground in Hawaii starting, right? Allowing this lava to flow through, these openings in the ground, splitting in the ground, allowing the lava to flow up. Somebody else said, in biology, we've talked about cellular fission. What does that mean? It's another word for that. Mitosis, splitting, the cells splitting up. Fission means splitting. Nuclear fission means the nucleus is splitting. You got one heavy nucleus that splits into two lighter nuclei. Now, here's an example of a nuclear fission reaction. This is not by any means the only example. This is just the one example that I've put up on the board. You can see here that one heavy nucleus, in this case uranium-235, splits into krypton and barium. Now, there are some neutrons here and some energy here, and they're important, but they're not important in determining what type of reaction it is. They're important for something else that we'll talk about in just a moment. What I want you to look at in determining that this is a fission reaction is that one heavy, uranium-235, splits into two lighter nuclei, krypton and barium. Now, what are those neutrons there for? Let's look at the one on the left-hand side. Uranium-235 will eventually decay on its own, but it's going to take a long, long time for it to decay on its own. So we kind of get this going a little bit through an artificial process. We bombard the uranium-235 with a neutron. So one uranium-235 nucleus is struck by one neutron with a gun, basically, a neutron gun. And that neutron gets absorbed by the uranium-235 and for ever so short of a time becomes uranium-236. Then it decays into any one of a number of possible combinations, including the one that you see up on the board, krypton and barium. We need to fire this neutron at the uranium to get this thing going. Now, why are those three neutrons there on the right-hand side? Essentially to balance the equation. If they're not there, then the mass number doesn't balance out. Sometimes you see a fission reaction where there's three neutrons produced, sometimes there's four, sometimes there's two. It all depends upon what nuclei are produced, how many neutrons you need in order to make sure that it's balanced. Now we also have some energy produced there as well. How much energy is that? Looks like a lot, right? 200 mega electron volts. It's enough to, well, blow up a city or power a city if we're talking about electrical generation, right? Right? But it's not. 200 mega electron volts is actually a really small amount of energy. It's maybe enough to move a speck of dust. So how do you go from this to generating enough electricity to power a city or generating enough energy to blow up a city? We need to have a lot of these reactions taking place. Not just one or two or 10, but we need a lot of these reactions taking place. We need to move a lot of specks of dust here. To do that, we design this so that a chain reaction is sustained. What's a chain reaction? Well, when the products of one reaction cause more reactions. In this one, we have a neutron bombarding uranium-235, causing 3 neutrons, and 200 megaelectron volts of energy. If we set this up well, if we design this properly, then maybe we can get these 3 neutrons, each of them, to bombard another uranium-235. So maybe these 3 neutrons can cause 3 more reactions. Then we're going to produce 600 megaelectron volts of energy and 9 neutrons. Now maybe those 9 neutrons can bombard 9 more uranium-235, generating 27 neutrons and even more energy. 27 neutrons cause 27 reactions, 81 neutrons, okay, 243 neutrons, and so on, and so on, and so on. Within a small fraction of a second, we've got this exponential growth taking place in the number of reactions that we have. In other words, instead of moving 1 speck of dust within a tiny fraction of a second, we're moving this exponential number of specks of dust. And we're generating enough heat to generate enough electricity to power a city, or we're generating enough energy to blow up a city, as the case may be. Now, doing this is easier said than done. It's not just a matter of, hey, you got all this uranium, and we just get her going, and it just goes. It just does what it does. It has to be designed so that these neutrons will bombard the uranium. The other aspect of it is that there's so much energy generated so quickly that in many cases it'll blow itself apart before these neutrons have a chance to bombard more uranium. That's what happened in the bomb that was dropped on Hiroshima in 1945. Do you know that the Americans used about 50 kilograms of uranium? That's it. About 50 kilograms of uranium in that bomb that blew up Hiroshima. 50 kilograms. Okay. Most of you weigh more than 50 kilograms. Maybe all of you weigh more than 50 kilograms. And remember how dense uranium is. Uranium is way more dense than you. Even though sometimes, we look at stuff on the board and it looks like, oh, I don't understand that. I feel dense. Like, uranium is way denser than you are. It's like this much uranium. They dropped on Hiroshima and it blew up a city. And here's the kicker. It wasn't even close to 50 kilograms that exploded. We don't know exactly how much exploded, but scientists will estimate that it's somewhere between 3 and 5 kilograms of uranium that actually exploded. Like 3 to 5 kilograms, 10 pounds. Like your desk weighs more than the uranium that exploded to blow up a city. Why was that the case? Well, the chain reaction was sustained until there was so much energy generated from this chain reaction that the bomb literally blew itself apart, and the other 45 kilograms of uranium couldn't react with the neutrons. They expected that. That wasn't a surprise. They expected that to take place. But that's the nature of the beast, right? You get this chain reaction taking place. You can't hold it together. Okay, you can't hold it together. So fission, splitting. Heavy becomes light. 1 becomes 2. Chain reaction sustains. This chain reaction is sustained by having more neutrons on the right side than we have on the left side. The other type of reaction that I want to talk about today is called nuclear fusion. Fusion is a reaction where 2 light nuclei fuse or come together to form 1 heavier nucleus. Notice I didn't say heavy, I said heavier. An example, one of many examples would be this one, H2. This is a heavy isotope of hydrogen. Normal hydrogen is H1, 1 proton, 0 neutrons. This is 1 proton and 1 neutron. These things fuse together. They come together to form 1 heavier, right? 2 light form 1 heavy, and a neutron and some energy. this process, this energy is released. Again, not a lot of energy, not a ton of energy, but energy. This isn't enough to do much, so we have to get lots of it going. How do we get lots of this going? Well, it kind of comes about from the difficulty in making this thing happen in the first place. This is really difficult to make take place, really difficult. Happens naturally in the sun all the time, but it's difficult to make this take place ourselves, to artificially make this take place. Here's the reason. Hydrogen nuclei have a charge, both of them have a charge that is positive. When you bring positive close to positive, what happens? They repel. And the closer they come, in other words, as R becomes smaller, F becomes exponentially larger. So that force of repulsion, as these two nuclei get closer and closer together, becomes bigger and bigger and bigger, right? We have to overcome that force of repulsion. And in order to overcome that force of repulsion, we need to pump energy into this. Energy usually in the form of heat. That's why this sustains itself in the sun, right? The sun is really hot. It's a nuclear furnace. It's got all this hydrogen in there. And this hydrogen fuses together because of all this heat that helps this hydrogen to overcome the forces of repulsion. In a similar way to the way neutrons help sustain this reaction, the products or the neutrons help sustain fission, some of the energy from this reaction can go into causing more hydrogen to fuse, producing even more energy, which can cause even more hydrogen to fuse, and so on. Again, in order to make this any measurable, really amount of energy coming out of it, we don't need one of these, though. We need a lot of them. And we get a lot of them by setting it up so that we'll kind of kickstart it going, and then it has to sustain itself, basically. Yeah. Does that make some sense? Now, which one of these two do you think generates more energy? Fission or fusion? Fission? Okay. The fission, I'd say the fission bomb, two fission bombs were exploded in 1945, right? The first one was, I always get mixed up which one was which, but I think the first one, which I know was in Hiroshima, I believe that was uranium-235. And the second one that was dropped a week later in Nagasaki, I think was plutonium. The uranium bomb, using uranium-235, the plutonium bomb using plutonium, I forget what the isotope of plutonium was, 1945. The H bomb, the hydrogen bomb, the first fusion bomb, was developed by the Americans in 1952. Which one do you think is more powerful? Fission or fusion? Well, it's a bit of a loaded question. Okay? Some people said fission, some people said fusion. Well, you're both kind of right, actually. If we look at a single reaction of fission versus fusion, fission will produce more energy and fusion will produce less. So if you have one nucleus of uranium-235 and it is bombarded with one neutron, and you get these two products out of it plus some extra neutrons, and the energy, that energy will be greater than the energy produced in that single fusion reaction. So were they taking a step backwards to develop the H-bomb in 1952? No, it generated more energy than the fission bomb did. So how do we justify that? Well, if we look at these two reactions right here, first one being fusion, right? We got two light becomes one heavy. The second one being fission. We have one heavy becoming two light. If we look at these two reactions, there is way more reacting in the fission reaction, right? Uranium-235 with a neutron, that's 246 protons and neutrons. In the fusion reaction, we have how many protons and neutrons? 4. So there's way more to react in a single fission reaction than in a single fusion reaction. If we take a kilogram of this and we take a kilogram of this, now which one generates more energy? Fusion, by a long shot. So remember, if you're asked a question about the energy released, and there's a decent chance you will be, remember that if you're talking about per reaction, fission makes more because there's so much more mass involved. But if you're talking about, if you're comparing apples to apples and comparing 1 kilogram of a fission reaction to 1 kilogram of a fusion reaction, then the fusion reaction wins. Now, finally, it's the last thing that I want to do with you today. Both of these produce byproducts. Fission, you can see that in the fission reaction that I have here, it produces krypton, barium, some neutrons. The fusion reaction I have here produces helium-3 and neutron. They both produce byproducts. The risk of the byproducts of fission is high. These byproducts are highly radioactive. So the bomb that was dropped on Hiroshima in 1945 killed a lot of people instantly. It blinded people because of the amount of light that was generated. People that were looking right at it would have been blinded instantly. But it also caused problems for several years after it, long-term effects, development of cancers because of exposure to ionizing radiation that came from the decay of the products of the fission reaction. Like, you didn't really want to be anywhere around there for a number of years. It wouldn't be so bad now, even though there would be some remnants of that still there, but you wouldn't have this incredibly elevated risk of anything now because we would have had enough decaying before now to make it relatively safe to be there. But for a number of years afterwards, it would not be a good place to be. Now, here's the kind of a little less understood aspect of it. The products of fusion reaction, even though this explosion would be much greater and a lot more heat generated and a lot more chance of blinding and instant catastrophic injuries or death, the byproducts are actually relatively harmless. So as much as the H-bomb would have killed more people instantly in Hiroshima than the atomic bomb did, than the fission bomb did, people could return to the area quicker after the detonation of a fusion bomb than they could after the detonation of a fission bomb. Does that make sense?